Welcome to transfer functions and the general formula for the solution to an IVP. So recall in the previous video, we found the formula for solutions to IVPs of the form y double prime plus 5y prime plus 4y equals f of t, with initial conditions y of 0 equals k naught and y prime of 0 equals k1. So now we're going to generalize this even further, and instead of having a specific homogeneous component to our equation, we're going to consider the generic second order linear differential equation with constant coefficients. So now let's consider IVPs of the form ay double prime plus by prime plus cy equals f of t, with initial conditions y of 0 equals k naught and y prime of 0 equals k1. So we get a theorem for the solution for this. So our theorem is that the IVP ay double prime plus by prime plus cy equals f of t, with initial conditions y of 0 equals k naught and y prime of 0 equals k1, has solution y of t is equal to k naught times y1 of t plus k1 times y2 of t plus the transform of f with omega evaluated at t, where y1 satisfies the homogeneous equation ay1 double prime plus by1 prime plus cy1 equals 0, with initial conditions y1 of 0 equals 1 and y1 prime of 0 equals 0, where y2 satisfies the homogeneous equation ay2 double prime plus by2 prime plus cy2 equals 0, with initial conditions y2 of 0 equals 0 and y2 prime of 0 is 1, and where w of t is simply 1 over a times y2 of t. So essentially what we get is we can find the generic formula for any IVP by solving these two homogeneous IVPs and then building our formula with that convolution of f and this w. So this gives us a quick way to solve any IVP with constant coefficients where our f of t is likely going to be changing and our initial conditions might be changing. So we can get a formula then. So for a quick proof of this, or a proof sketch at least, we'll do a proof sketch. So if, again, we have suppose that ay double prime plus by prime plus cy equals f of t with initial conditions y of 0 equals k naught and y prime of 0 equals k1. Then let's suppose also that y1 satisfies, again, ay1 double prime plus by1 prime plus cy1 equals 0, with y1 of 0 equals 1 and y1 prime of 0 equals 0. We know that this solution exists, right? So we can find such a solution. And suppose, let's say suppose y1 is the solution. To the homogeneous equation we have here. And then let's suppose y, or homogeneous IVP as stated earlier. Let's suppose that y2 is the solution to ay2 double prime plus by2 prime plus cy2 equals 0, with y2 of 0 is 0 and y2 prime of 0 is equal to 1. Then let's consider all of our Laplace transforms. So note that if we take capital Y1 of S to be the Laplace transform of Y1 of T, we have A times S squared Y1 of S minus S times Y1 of 0, which is 1, minus y1 prime of 0, which is 0. Then we have plus b times s times capital Y of s minus 1, since y of 0 was 1. I'm going to shift this to the side a little. Plus c times y1 of s. This should equal 0, since we are working with that homogeneous equation. And so we get that y1 of s is equal to, we would have an as plus b would be added on to the right, and then we would divide by as squared plus bs plus c, solving for y1, capital Y1 of s. Similarly, if we set y2 of s, capital Y2 of s, to be equal to the Laplace transform of y2 of t, then we have a times s squared y2 of s minus s times 0 minus 1 plus b times s times y2 of s minus 0 plus c times y2 of s is equal to 0. Solving this, we wind up getting our capital Y2 of s is equal to, we would just have a as the only constant term there, divided by s squared, as squared plus bs plus c. Now, if we go ahead and take the Laplace transform of our capital Y so the Laplace transform of our original equation. So now, taking the Laplace transform of the original equation, we have, we would have A times y double prime. So A times s squared y of s minus s times y of 0. So s times k naught minus y prime of 0. So minus k1. Then we have plus b times s times capital Y of s minus y of 0. So minus k naught. And then plus c times capital Y of s. And all of this should be equal to the Laplace transform of f of t, or capital F of s. This becomes, we have as squared plus bs plus c, all multiplying our capital Y of s. Then we have plus a times k naught times s plus a times k1 plus b times k naught equaling f of s. And so we get our capital Y of s. Oh, sorry, those should all be minuses. We should have minus an a k naught s minus a times k1 minus b times k naught. So this becomes, we have a times k naught times s all over a times k naught times s plus a times k1 plus b times k naught all over as squared plus bs plus c, and then plus a capital F of s all over as squared plus bs plus c. This first fraction we could rewrite as our capital Y of s is equal to k naught times as plus b all over as squared plus bs plus c. Then we have a plus k1 times a over as squared plus bs plus c. And then we have plus a capital F of s all over as squared plus bs plus c. I apologize, I need to update my screen. Okay, so we have our k naught times as plus b over as squared plus bs plus c plus k1 times a over as squared plus bs plus c plus f of s over as squared plus bs plus c. Now, if we recall, we had forms for y1 of s and y2 of s. So if we recall, y1 of s was as plus b over as squared plus bs plus c, and y2 of s was a over as squared plus bs plus c. We can use that to substitute in and get an alternative formula for capital Y of s. So writing Y of s in terms of y1 and y2. We have capital Y of s is equal to k naught times y1 of s, right? That is y1 of s is precisely what was multiplying k naught there. What's multiplying k1 is precisely our y2 of s. So we have plus k1 times y2 of s. And then what's multiplying f of s is 1 over as squared plus bs plus c. And that's just missing that a from the numerator of y2 of s. So we could write this as 1 over a times y2 of s. That'll be 1 over a times a over as squared plus bs plus c. The a's cancel out. We get precisely what we wanted. times f of s. So if we set, now let's call w of s is 1 over capital W of s is 1 over a times y2 of s. Then we have capital Y of s is k naught times y1 of s plus k1 times y2 of s plus w of s times f of s. And if we now take the inverse Laplace transform, so taking the inverse Laplace transform, we get y of t is equal to k naught times y1 of t plus k1 times y2 of t plus the convolution of f of t and w of t. Or in other words, we have y of t is equal to k naught times y1 of t plus k1 times y2 of t plus the definite integral from 0 to t of f of tau times w of t minus tau t tau. We could also swap the order and do w of tau times f of t minus tau d tau. But so this is our ultimate theorem, our ultimate equation that we had. And so our original theorem, our original statement was that we could write it by the convolution, and these are the forms. So again, this gives us an alternative format. So just note that k naught times y1 of t plus k1 y2 of t is independent of f. So we'll call this v of t equals k naught y1 of t plus k1 y2 of t. So I'm just going to write that actually earlier. So if we call this v of t is the k naught y1 of t plus k1 times y2 of t is independent of f. Then if we call h of t that f star w of t, the convolution of f and w, this is independent of the initial conditions. For most physics problems, oh, before we do that, y of t is just v of t plus h of t. For most physics problems, that v of t will go to 0 as t goes to infinity. We have seen, right, for the spring systems, for the spring mass systems and for circuits, that part does go to 0. And so we call that v of t the transient solution. H of t we call h of t the steady state solution. And we call W of S the transfer function. So we call capital W of S the transfer function. The reason behind that is if we have our h of S, so our h of t is the convolution of f of t and or the convolution of f and w. Capital H of S is capital F of S times W of S. And so this gives us then that W of S is H of S divided by F of S. So it's the ratio of the steady state of the transform of the steady state solution to the transform of the forcing function. So what becomes useful for this is that transfer function is independent, that W of S. So because W of S was just 1 over A times Y2 of S, W of S is actually independent of the forcing function. It is also independent of the initial conditions. And so if we have a target steady state, we can use this transfer function to figure out what our forcing function should be. So if we have a desired steady state solution, then we can use W of S equals H of S over F of S to solve for the desired or to solve for the needed forcing function. So W essentially is what is useful for transferring us from forcing function to steady state function, and we can use it to solve for what one or the other should be. So this is sort of the generic formula for a solution to an IVP, as well as the transfer function and how we can sort of pick out the needed forcing function to hit our target steady state solution.